Ah, there we go. Okay. I should be online now.
Yeah, I got volume too.
You can hear me? Cool.
Yeah, you're good.
Nice.
Okay. We want display plus desk cam. There we go. That's what we want. All right. So we're gonna add a couple more servos here. D2, D3.
So I'm supposed to talk into the bottom or the side of the mic? I forget.
Side.
Side, right. Whoa, that's loud.
You need to pull your cover off. You can see the flat.
Okay. Cool. Do 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 do.
Let's just do 115 and let's go.
Perfect.
Two.
Perfect. All right, let's start this. Boom, 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 boom. Let's see here, close up. Hey guys, hope everyone had a good summer. I've been gone for a while, and I'm back. We're gonna do some hacking right now. I've been paying attention to the forum, obviously, for a little bit this summer when I was working on some other stuff. Some questions came up, and I figured I'd just tackle this particular one because I thought it'd be. Oh, hey, Will, thanks for welcoming me back. I figured I would do this one sensor because I thought it was pretty intriguing. Jeremy's been asking me to do it for a couple of years, actually. It's been on a shelf, sitting there, waiting and waiting and waiting for me to get around to it. So since somebody mentioned it online, I thought it'd be pretty cool to play with. This is the AMG, AGM, AMG 8833, and it's a thermal camera. So I don't think it's like super great resolution. What's it, like 9x9 or something like that? But we'll see soon anyway. So tonight is going to be not super exciting because I'm going to spend a lot of the time programming, and I guess we can chat and listen to Jeremy's open source music with commercials because he refuses to pay for Spotify. so hopefully the commercials aren't copyrighted and we get this video pulled off YouTube. But either way, it should be a fun night. I'm gonna chill out and then ease into this. So the first thing I need before I start, though, is I need to get myself my usual Friday beverage to begin. So let me go do that, and I'll be right back.
How I'm gonna loosen this bad boy off. Maybe I'll just use my trusty. Or sorry, what do you call these things? Wire strippers. There we go. Yeah, that did it. Okay, so I think this might be wired backwards. Unfortunately, I don't know how that happened, but it happens, I guess. Unless I just chose the wrong value. See how it goes. Plug it back in and see where it ends up. So that was D3, okay. So we'll plug that into D3 and see what happens. I think I released it already, so.
Cool. Okay. Well, today's episode is brought to you by a beer you probably have never heard of called Maclay's. It's a Scottish beer. And it's kind of funny because where my cabin is in the summer when I spend it with my family, this is the beer that I drink, which I don't know where else you can get it. I've never seen it anywhere else in the world. So this is what I'll be drinking tonight while we do this. Cool. It's nice, refreshing. Okay, cool. So this sensor, before I guess we start, I'm going to explain what we're going to do. On this board here, this is the OpenCM. I'm only choosing to use this particular board because the person who asked about this sensor is using this board, and I don't have the firmware supporting I2C right now on this board, which means that it can't use the sensor. The EasyB from Easy Robot, of course, has I2C, so the plugin that we'll create tonight will work with any of the boards that support I2C. So we're going to first add I2C support to this board. And once we do that on the firmware, then we can save the firmware on the website, and then we can use this sensor on that board as well. I don't know what we're going to do with it. It's it's a thermal camera. I don't have any ideas yet. I know Jeremy thinks it's intriguing. Maybe one of you guys will have some ideas, but we'll play with it once we get it working and see what it's like. So the first step we're going to want to do is just give this thing a connection to the computer. So we'll plug in the USB into this, and then I have a USB hub here. There we go. Now it's not going to be super exciting to see this while we're programming it, but I'll put the camera close to it so people can see what we're going to be doing. And I'll switch over to the desktop. Here's my life hack. So we're going to be using, like I mentioned, the firmware from the OpenCM, which is a Robotus product. So it's going to be in our list of microcontrollers right here. And you can download the firmware here. So last time it's been updated was April 8th. I'm not going to download it and edit it from here because I have a copy on my computer. So let's just go to my computer here, and there's the OpenCM. Looks like I've made a change to it recently. Let's see what that is. So I've you move your mic closer. Oh. Jeremy and I are both doing our hacks. Oh God, here's a Spotify commercial, our first one. You know what? We can play a drinking game every time a Jeremy's Spotify commercial comes on. I can drink.
It's from the government of Canada.
My tax dollars at work. Government of Canada advertisement. So it looks like I added some comments here and some other things. So this is open source music.
That's another commercial.
Oh, so whatever I've added as code is not going to affect the I2C thing here. So let's just load this up.
I think that's as far from open source as you can get. Metallica.
Yeah. That definitely is going to get you triggered. Yeah. Are you drinking too then, Will? We're going to play the drinking game together. I'll send you a McClay's. Okay. So here, it's going to be hard for you to read. Let me see if I can make the font bigger. Oh, that's the wrong way. How do I make it bigger? Oh no, what did I do? Come on. Arduino, you could do better than this. Oh no. This is so small. What did I just do? I really broke it. Maybe I should go grab a mouse. Maybe it'll be better than this trackpad. 1 sec. Look how small the font is.
Whoa! No. Alright, just removing the hot glue to get this potentiometer off so I can resolder the wires on it. Really, I just need to take the hot glue off the wires and then be fine.
Okay, let's try this. Oh man, computers are hilarious. I don't know why more people don't do like computer comedy shows where they could just like use the software and people can laugh at how broken it is, especially if it's like Word or anything open source. Not saying Word's open source, but it is a Microsoft product. Okay, so these are the commands that the EasyB protocol for Easy Builder supports, and you can extend them, of course, by using 0. There's a tutorial on doing that. Now, we're not going to have to do that because we already have I2C read and write commands. And there should also be an I2C init as well. Here it is, clock speed. Okay. Now, the only thing is, and I was told this today, is the Arduino shares the I2C ports with the analog ports. Right, Jar? Yeah. That being said, I'm guessing what we'll do is maybe we'll do is modify the code so if an analog voltage is red, then we'll put it into analog mode. And if any I2C stuff is happening, we'll put it into I2C mode. Because we want those ports to be usable for everyone, right? We want it to be very versatile. We don't want the 2 analog ports to be turned into just I2C, and then everyone who has to use this board sacrifices two pins from analog, just because it's I2C. So we're going to try to make it versatile. So first thing we want to do is let's just add support for setting the clock speed. Okay. So we'll copy this command here. And let's take a look. Down at the bottom of the code. Okay, so in here we have what's called any command that's called EasyB4. So these are extension commands to the protocol because there can only be so many commands on the base level of the protocol. So we go one level deeper. So if it receives one of these, then it receives another command, which is your layer 2 command. And you can see here we have stuff for the UART. And reading. So at the bottom of this, right here, we'll just go else if command 2 equals this. And this gives us, now we can do the clock speed. We are going to want to check the protocol for... Actually, I think I have... We can download it. Where can we download it? Oh, I know where we can download it. The EasyB datasheet has a published communication protocol. Here we go. And here's the communication protocol sheet here. Boom. Nice. So if we look at... Let's see, there should be an I2C clock speed. There it is there. Page 7. Okay, so it expects a 32-bit value. Little Indian. So that's what we're going to get. So the EasyB is going to transmit a 4 and 11, which we know that because I2C clock speed, this is probably an 11, right? No, it's a 17. Oh, 0x11. That's hex for 11, or for 17. Yeah, so that's right, 17. Boom. And then it's going to send an unsigned 32-bit, which is the speed that the I2C clock's initialize at. So we want to read, I think there's a command already here called read 16. So we can go uint 32. We'll say speed equals read 32. I believe this exists. Let's find out. Read 32. Oh yeah, she does. See? So it's just reading each byte, and bit shifting each one as it goes, and then assembling it into just XORing it, right, into int 32. So this will give us, how do you auto format on this? Just right click? Okay. There, so that'll give us a speed, and now we want to initialize I2C. I have no idea how to use our RTC with Arduino. Arduino I2C. Let's find out.
I think it's the wire library.
Oh yeah, look at that. Wire. Okay, there's a begin. Set clock. That's what we want. What's begin do? Initiate the wire address to join the I2C bus as a master or a slave. Should only be called once. Okay, do we have to call this when we change the clock speed though? There's no information here about that. Well, it says under begin, it says should normally be only called once. So let's let's not care. Let's just go wire.begin, and then let's go wire dot. Let's take a look at the set clock. Set clock. Oops, small, lowercase. It's not highlighting. And it wants the frequency. Well, let's just take this dunk, 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 and put it in here. Boom. Will that compile? Let's see. Let's see if it compiles first to know if it's going to actually work or not. Wire is not declared. Do I have to do one of these include wire things?
Yep.
Now let's see. Nice. Okay, we compiled. So this worked. So that's one command done, which is set the I2C clock speed. And next, we want to, let's look back at our document we had open here. We want to read I2C. Here it is here. So we have read and write. So let's do write first, since it's there. So write data out of the I2C port on the EZB. Okay, so what this means is that the EZ Builder is going to send data to the EZB controller, and then we're going to be writing that out over the I2C line. So all it cares about is 0x0a, and then the 8-bit number of bytes to send, and the data bytes. That would make sense, because you can't send more than 8. Actually, I don't think you can send 255 characters. I think you can only send it in chunks of smaller, right? But anyway, so let's do that. So we want to, here we go, I2C write, which is command 10. Command 10 is A in hexadecimal, right. So we'll go back down to our commands, different ports, and we'll just throw this in kind of anywhere, right, but before it gets to the EZB thing here, right there. So we'll go else if cmd equals write. And while we're here, let's make this read. Cool. So we want to read how many bytes to send. So we'll say bytes to send. And it's a, I think it's get byte, read byte. I can see it right here. Booyah. And then we want to send them out. So how do we do that? Let's look back at our wire class. Right, there it is here. Begin transmission. Begin a transmission to the slave device with a given address. Okay, so that should already be included inside of, so that would be the first byte of the, there we go. Yeah, so that would be the first byte that it's going to read. So what we're going to want to do is say bytes to, oh sorry, wire dot, was it begin transmission? Begin transmission. The address is going to be read byte. Right? Because the first byte that we're going to get back after this is going to be the we're going to send to, and then we want to do this thing called write. Writes data from a slave device in response to a request from a master. Oh. Or queues bytes for transmission from a master to slave device. Yeah, there we go. Begin transmission. And then write the value. And then end transmission. Okay, so now we want to go for x equals 0 to, oops. Actually, I think we do that right here. Oh, we're using way too much memory there. We don't have to go use that. 0, x is less than bytes to send, minus 1, because remember, we already sent the first byte, which is this. And now we want a wire dot write read byte. And then we want a wire dot end transmission. Sounds like a KLF song. Begin transmission, end transmission. Isn't
Roman Jules, the band, the artist?
No, I'm talking about like when you talk about begin transmission and end transmission. Wasn't there a song from KLF where they were talking about like, oh, last train to Trans Central? Okay, so that's our write. Now let's do our read. So let's check out what read looks like here. So join the bus, which we did. Request from slave device. Okay. So let's take a look at the...
Okay, good enough. Let's heat shrink those.
Too many windows open here. Okay. So read. Read requests the number of bytes. So essentially it's the same thing. We just got to say bytes to read equals read byte. And then, according to this, while wire.available, slave may send less than requested. Interesting. I don't like that very much. I hope it doesn't send less than requested. If that's the case, we're going to have to fill in whatever wasn't sent with nulls, if that's the case. But let's find out first. So now we send, so we want to send data back out. So this is it, right? I'm just going to figure out how we write back to the EZB. I need an example of that. We have read byte, I know. Oh, here we go. Just communication port dot write. Oh, wow. Communication port dot write. Wire dot read. And we want to do this as many times as is loops. So we'll do the same thing here. For byte, x equals 0, x is less than bytes to read, x plus plus. Boom. And then what we'll do is we'll say while if wire dot available, we'll read it. Otherwise, we'll communication port. We'll write 0, just a null. Okay. And then that's it. We don't have to close or open any connection at this point. Or any transmission, I mean. So that's good. So let's take a look at our code. So reading or writing, we'll read how many bytes we're supposed to send. And then what we'll do is we'll read the very first byte. And then we'll throw through the rest of the bytes we got here, -1, because we sent the first one out. Reading bytes and sending it off out the wire. And when it's done, we end the transmission. To read bytes, what we'll do is we'll say how many bytes are we supposed to be reading, because the EasyB will tell, or the Easy Builder will tell us. We'll loop through that number of bytes they want to be read, and if there is any bytes available, we'll read it. If there isn't, we're going to write back just a null. That way Easy Builder gets something back, so it doesn't just hang forever waiting for no data. So that should be good. Let's see if we can upload and compile this thing. See what happens. It takes a while, so... Ooh, darn it, I was just about to have a beer, too. The overload is... Okay. Probably because a 0 could be any value, right? Might have to cast that as a byte or something. Yeah, let's go like this. Byte. It's kind of funny to have to do. The compiler should be smart enough to know how to do this. Oh, I failed to open the COM port. Oh, I don't have any ports open, it says. Maybe my hub is being too consumed with the datas. It might be. Yeah, it doesn't look like I'm going to be able to get it. Let me try plugging this into a different port on the hub. Let's see if this works. Huh. I don't even know if the port will refresh. I might have to close it down and reload it again. I don't have a lot of confidence in the Arduino IDE. I did once install this like Arduino Visual Studio plugin, but that was a really bad idea. I thought it was going to be good because it was Visual Studio, but it was terrible. Okay. Let's try plugging this directly into my computer and bypassing the hub. The only problem is I'm going to have to unplug my mouse. I'm going to have to use the trackpad again. Let's hope I don't mess up the font size. Okay, how about now? Oh, there we go. COM6. Ooh, fancy pants. Okay, we'll upload the sketch. It takes a bit, so I'll drink some beer.
Okay, we'll see what happens when I flip it again. It's 20. We have the value of 29.
All right, it is uploaded. Okay, so we should now be able to load Easy Builder. And it should work. Let's see what happens. So let's connect to COM6. Connect. There we go. We'll copy the debug data and let's paste it in Notepad because I always like to do this. Okay, so you can see here that we connected to the OpenCM and we have the ability to do I2C. Golden. Now let's add a script. Booyah. And oh, do you know what we should just check before we edit the script? Let's look at this data again here. Huh. I don't see it saying anything about setting the I2C clock. Huh. I wonder if there's a capability that's missing from it. We can figure that out later. Okay, so let's go back into our code here, and we should be able to write I2C What are the I2C commands? I2C clock speed, I2C read and write. So I2C write, the board index, the address we're going to write to, something like that, and some data. Now, we have nothing connected to it, so I don't know what that's actually going to do. It might even disconnect, but let's just hit start and find out. Are we still connected, do you wonder? Let's find out. Let's read some ADC data and put up a graph here. Yeah, it looks like we disconnected. So because there's nothing connected to the I2C device, it was not happy. That's expected. Can we connect? Let's pause this. Let's connect again. Will it let us? We might have just locked up the device. Yeah, it looks like we locked up the... So let's unplug the power to it. Power back in. Let's try this again. Okay. And can we read I2C? There we go. There's I2C data. Wherever the I2C stuff is on here, we should be able to rub our finger around it and see data happen. There we go. Somewhere around here. Cool. So by trying to write to a device that doesn't exist, we locked it up. Not a surprise. I don't know if there's even a way to check if it was begin transmission, right, end transmission. Yeah, I don't know if there's even a way for us to check if the transmission was successfully written. Therefore, we could have recovered from this, but that's okay. We would normally expect there to be a device connected to it anyway. I2C is kind of finicky that way. So let's check out our... Where's our code again that we just did? Port. I2C, here we go. I2C write. So boom. Just making sure that's right. Bytes to send -1 x++. Yeah, that should be enough. Bless you, Jer.
Make sure these are engaged with each other.
You know what we should do? No, this is good. Okay, so let's now connect an I2C device. So let's connect this thing to it and see if it works. I'm just wondering though. I wonder if we have another device we can use. Something that we actually know works so we can test it. Such as some RGB eyes from Easy Robot. That's a good idea. I don't have the pinouts for it. Oh, yes I do, because they're written right there. Let's see if you can see that. See? So if we give it some power, then we should be golden. I don't know how many volts Arduinos use. Are they 5 or are they 3? Oh, there's a 3.3 volt output on this. I don't know if you can see that on the camera. Hold on. One beer an hour is okay? No. I only had one beer, so we're okay. Actually, the laws in Calgary are pretty strict. You're only allowed to have, I think, one beer pretty much the whole night. So I'm not unfortunately allowed to drink that much when we do these live hacks. I'm having trouble focusing this camera. There we go. Okay, so you can... it's kind of bouncing around. You can see there it says 3.3 volts on the top up here. So that's what we're going to power the RGB eyes from. And then we have to figure out what ports the I2C is on. I don't see any reference to I2C. Oh, I do see. No, those are programming header pins here. Yeah, we might have to check some data sheets to see what's going to happen with I2C. I don't see it on this side either. Let's check Cynthium's website for the product that we're using, the OpenCM. I think there's a sketch drawing of some sort on there. There we go. Here we are. Okay, so here's our clock. Oh, here's a SCL and SDA. There we go. That's what we care about. So it's pin 24 and pin 25, which also is the UART 3. So by using the I2C, we're going to lose. Oh, wait, that's SLC 2. That means there must be more than one. Oh, my. What? Okay, I'm a little bit confused now because this says SLC2 and SDA2, meaning that there's more than one I2C device on here, which I would definitely believe. Should we check the code? And let's change this from wire to wire 2. Okay, we got wire 1, wire 2, wire 3. Let's just try building this, see what happens. Maybe there's a couple different... No? Okay, good. So it's just a really weird, not surprisingly weird documentation error, SCL2 and SDA2 here. So it's going to be pin 24 and pin 25. So let's throw... We want to connect it to this somehow. This pin here. So maybe the best bet for us is to... I might be able to get something in there. Let's see. See if I can get one of these guys in here. Oh. Not very well. It's kind of small. Oh, I did it. Okay, cool. So if we can put headers on here, and this is obviously the wrong size, but I can go with a female side on one side and a male side on the other. Okay, so I'll get the soldering iron going, and we'll do some soldering, put some female headers on there. All right, move things around. Whoop. And my good old solder holder. And let's see if I can get some. There we go. Lots of these little connectors. These are super useful. I get these off Easy Robot's website. They have, you can buy like a whole pack of these, and you come with different female to male, male to female. There we go. Nope. Okay, this one's a male to female. And it looks like I must go through males to females quite a bit. Oh, and this one's male to female as well, but it's a nice long one. Look at this one. It's a good one. Oh, forgot. We have to drink. It's a commercial break from Jeremy's cheap pocketbook who refuses to pay for Spotify. As we're playing commercials. Bum, bum, bum. Okay, here's another male to female. And... I have a lot more males to males than I do male to females. Well, I have 3 so far. I just need one more. Oh, I think I found it. It's a yellow one. There she is. Cool. All right. And now we just have to put some header pins on this. I think I have some. Oh, I have some right here. In this little baggie. This is my baggie of header pins. Don't tell the coppers. Keep a baggie of header pins. Okay. So power. Well, two that are beside each other for SLC and SDA, those are the I2C pins. And then we need power and ground. And it looks like the ground and 3.3 are right next to each other. Sweet. So we'll throw a third one in there for 5 volts as well. Just in case we ever do any 5 volt stuff. Okay. Let's do some. Well, first, okay, if you're ever soldering, guys, make sure you disconnect any power that's going to the wall outlet. If you want to solder something and you're really safe on a battery, fine, right? If you short it out, it's gonna be terrible. But if you go to solder when you're plugged into power, the ground that's shared across transformers and stuff, you can create some serious issues. So especially through your computer. Okay, so pin 24 and 25. That's way down over here. It's right above 5 volts. So we have a reference pin here. And then we have a 5 volt. And then we have 24 and 25. Right there. I'll flip this upside down. Clean my bit off. Because I like to solder at, 1,000 degrees. I like it 450. Oh yeah. Let's do this. I don't have time to wait for solder to melt. There we go. And now we decided that power was somewhere around here, up at the top. Oh, on this side. Oh, it looks like somebody had already been soldering here. There's a 3.3 volt soldered and a... Uh-oh. I'm not very good at soldering where someone else had soldered before. The holes are already filled. I'm going to blame Jeremy on this one. You might have to, Jer. If anybody wants to see me butcher a board, can you pass me a gun? All right, let's see if I can.
This one feels pretty good.
Yeah, this one doesn't feel very good. All right, let's see if I can gun this. Oh yeah, look at that. I emptied it right out. Let's do the next one. Oh. Huh, not a bad job I just did there. Cool. Let's see if I can get this to fit. Oh, I did do a bad job. I did a horrific job.
Yeah, still not engaging the plot.
Because I was doing the wrong side of the board. So I just cleaned off pins I didn't need to clean off. Here, I'll give you a closer look and see what I'm doing.
Seems like it's...
Hold on, we'll wait for it to... There we go. So this 3.3 here was clogged, just like this ground is. So I'm gonna
But it seems to be skipping off the front of the
put this against one side
gauging.
and the soldering iron against the other side. And then heat it up and then push the button. And it's supposed to pull whatever was in there out, but it didn't yet. Let's try it one more time.
Should be engaging. Very odd.
There we go. Take a look at that. See? So this just suctioned it out. And then you'll see there's the solder that was in it. Cool, right? Okay, now, of course, you don't want the solder around, because if you put your board down on it, so clean the solder away. And now let's throw this in here. Nice. We'll solder these in. See if we can get our focus back. There it is.
So either something's too short. I'm just going to do a quick test here. Well, it did actually change, but it doesn't meet up with this.
Cool. That should be good. That's all we need to do for soldering now. At least right this second, until we start playing with that other sensor. Okay, just as a recap what we're doing, we're going to hook up these RGB LED eyes, which are 3.3 volts, to the I2C of this, and see if we can actually get the eyes to move around. If we can, then we're golden. So here's our pinouts, which is it says ground and then VCC. So we'll make green ground, and then we'll make this color yellow here, VCC, so green is ground. That's way up here on these pins. So ground is here. And then VCC, it's 3.3 volts, so we want to make sure this is 3.3 volts, which it is, right in the middle. And then we have SDA and SCL. So we'll make SDA purple. So plug these in here. It's a tight fit. Jeez, get in there. There we go. It's quite the party in this little plug. Okay. SDA is purple, is what I said. Yes. So according to our board here, SDA is the bottom pin and SCL is the top pin. Cool. So let's put these so you can both see it. When I power this board up with some USB, we should see that board this light up into its default boot up mode. Here we go. Nice. I don't know if you guys are able to see that. There's nothing really diffusing the light, so let me try it again just to show you. See if you can actually tell what's happening here. Yeah, it's kind of difficult to see. Let me try diffusing it with, what do I have to diffuse it with? I don't have anything. I was thinking for a piece of paper. Oh, here's a piece of paper towel. Oh, yeah, look at that. Oh, do you see the flicker? Isn't that neat? So I can't see the flicker with my eyes, okay, like sitting here. But you can see the flicker in the camera. And the reason why, and I think I've talked about this before in a different life hack, is that because I wrote the firmware for this, so I know how I know why it's flickering. But like again, I can't see it here, and it's because the camera refresh rate is picking up the fact that only one of these LEDs is ever on at a time. So the power consumption of this particular board, even though there are 3 by 3, 3 by 3, right? So 6 by 3. So even though there are 18 RGB LEDs on here, okay, that means that there's 18 LEDs, and then there's 3 LEDs in each one of those. Okay, so there's 18 plus, so that would be 18 red, 18 green, and 18 blue. Okay, so what's that? 36, right? Or 32, 18, 36, plus another 18, right? What's that? Someone do the math for me. What's 36 plus 18? 46, 54. So there's 54 LEDs, but only one of those 54 LEDs is ever on at a time. And I'm not even talking about the red, green, and blue, like the whole physical LED. I'm talking about each individual LED that's even inside of it. So they're flickering really, really quickly, like this. And your eyes, so when I look at it with my eyes, I don't see the flicker, but through here I do. So the power consumption of this is very, very low. And that's what an issue I have with NeoPixels, because people loved the idea of NeoPixels, and so do I. The only challenge with them is that if you have 100 NeoPixels on a board, you have 100 LEDs on at once. And that draws a ton of current. And if you look at one of my other live hacks, you'll see how many amps, okay, not milliamps, how many amps, like up into like the, what did we get? We got like around 4 to 5 amps for one of the NeoPixel boards that we had to run. Okay, that's ridiculous. It's such a huge waste of power. So what is the alternative? Really, there really isn't, unless you're going to get into the low level coding for something like this. So just to let you know, though, this is why things that a lot of companies will make, like TV screens, LED screens, your phone, all these type of things, are so efficient, is because they will only do what they need to do fast enough for the human eye. Now, your dogs might not be happy with it, and your cats, right? Especially an eagle flying over, it'll see it as a flicker, because they have super fast refresh rates in their eyes. But us humans, we don't see that. Okay, so anyway, so let's fast forward. So now what we want to do, based upon how this is all hooked up, we should be able to return back to the software. And in, close on a or ADC here. So we'll connect to it. Okay, we did connect to it, successful. Now we should be able to add the RGBI, here it is. Which one is it? This one here, RG8x8. No, RG Animator, this one here. And now we should be able to click on the gear for this, create a new action. We'll just call this test. And we'll create a new frame. And we'll click on one of these, and I should be able to slide this dial. And it's not working. Okay, so this is moving. We should also see the LED on here changing, and it's not. So something's wrong with our code. So let's save this project anyway, so we don't lose it, and we'll call this OpenCM I2C test. All right. Now let's try reading an I2C or a digital port. Oh, gosh me. Sneeze coming on there. Okay. So this will allow us to be able to just read a digital port. In this case, it's 8 for whatever random reason. And there we'll know if the circuit board is locked up or not. So we did lock up trying to write to the board. And let's just verify our wiring here again, because we might have to get the scope out to see if data is actually being transmitted correctly. My chair keeps sinking. This chair in the lab is not the best for me. Maybe it's a sign I have to lose a few pounds or something.
You just got back from summer, man. David Hasselhoffing on the beach the whole time.
Was I David Hasselhoffing on the beach?
Yeah.
Yeah. And then I went and drank 3 beer and then did it again. The beer is the issue. Beer's not as bad as ads in Spotify, Jar. Okay, so let's look at our code one more time and just make sure everything looks safe. Okay, so I2C write, we read the bytes. We begin transmission on the first byte that we read, all right? And we know that's the address that we're going to be writing to. And then we write out the bytes that we read.
Definitely making a connection.
-1 because we did the first one. So this looks fine with me. And then we write out each one and then we end the transmission.
Let's see what happens when we
Okay.
put it in.
I wonder if we should take a look at where's the EasyB firmware? I know that is the EasyB firmware on GitHub?
Yes.
Yeah, let's take a look. Let's jump into GitHub here for Cynthium GitHub. And let's take a look at the EasyB firmware and make sure that we're kind of doing the same thing as what the EasyB from EasyRobot is doing. Their main board is what we want here. Firmware, source code. I don't see an I2C, but I know that it's inside of LED Blink. So there's a joke that we had back in the days of EasyRobot is when you created a new project in Visual Studio, it would always default calling it LED Blink, just I guess because people love to blink LEDs because they want Arduino users. And we just stopped renaming the files, the default files. So every project is LED Blink. It's pretty funny. So let's go down to our communication protocol here. So I2C. Let's just do a search in here. I2C write. There it is. Okay. So we have I2C write, our start. So this here is our I2C get address. Oh, interesting. Hey guys, I think that this documentation that we were following is incorrect. I2C write is this in the bytes to send and the data bytes? No, it looks like it's incorrect. Good thing we checked this open source code here from EasyRobot days of EasyB. Because it looks here is that we read the address, okay? And then we get the payload size and then we send. So our code is incorrect. So let's go back into this, remove this -1, and the bytes to send is after that, right? Just to refresh what we're talking about here, we get the address, which is here. Then we get the payload size, which is here. And then we send out each byte as we get it. Cool. So this is great. This is awesome now. Cool. So let's, we probably have to take this and turn the power on and off because we most likely locked it up. And let's program it. I don't know, guys. I might break my rule and have 2 beers tonight. Might be here for quite a while. All right. Looks like the upload has been completed. And Let's jump back into Easy Builder and we'll connect. All right, we connected. Now let's go into the RGB animator. And you can see here that we're reading data. This is good.
Sorry if I was off the screen there.
And oh, it didn't look like anything changed here. I don't see any changes.
Use the accelerator to make sure that gets glued on there quickly.
Now this is still showing that there's D8 is still running.
Okay, we're going to use that for the other servo assembly.
So we didn't disconnect, that's for sure. Because you see this D8? I don't know what port D8 is, but it's, you see I put my finger on it and it changed.
One more time.
So D8's over here someplace. Right? So we didn't disconnect, but we didn't communicate with this. That's for sure. So the next question that I have is, are we actually writing out on the I2C lines? Are we doing that? Is that the thing that's happening? Let me think to myself. Let's look at our code again. Oh, you know what, guys? We're not. Do you know how I know we're not? Because we never set the clock speed. Remember we did the wire.begin? So let's do this. Let's create a variable at the top of our program. Okay.
We'll just hot glue that. Hot glue isolate it.
Where are we going to put it? I'm going to put it... I'm just going to put it here. I'm going to say bool I2C initialized is false. All right. I like things to be capital when they're like this, but whatever. So what we're going to do is we're going to say, this way it's only initialized once. We're going to follow that little rule that we read on their page. Remember it said here under begin, you shouldn't do it very often. It said that here, this normally should only be done once. So let's only do it once. So if we initialized it, begin. And then we will set I2C initialized to be true. Okay? The very simple little way to know that it's been initialized. So if it hasn't been, we begin it. So let's copy this code and let's go up to our I2C command here. And let's put it here, the exact same thing. And let's put it here in a read as well. Why not? That way we can ensure that I2C has indeed been initialized with that .begin when any of these commands get run. And it's only going to be running one time. So let's disconnect from here. This goes black, telling us that they can't read anything anymore. And let's upload. I feel like we're getting close, guys. This means we might be writing to the RGBs pretty soon. Now, if this doesn't work, the next thing we'll do is we'll have to hook up, I think, a data analyzer to it. And we'll just check and see if there actually is data going across. All right, put that over top. And let's jump into Easy Builder, connect to it. We connected. We can see some, let's go into here. Let's configure our, okay, let's grab our this and let's move it. Okay, we don't see any colors. No, we do not. All right, we're getting closer though because we're not locking up the, uh-oh, what's this error? Oh, that's just not an error, it's a message saying we just saved. There, so this is still working. So if I put my finger over top of this, Yeah, see? It's turning red when I ground it out. So we're still connected. All right. So our I2C right. Let's take another look at it. So if we receive it, we check if we're not initialized. If we're not initialized, we begin, wire.begin. And we set it to true, therefore we never have to initialize again. And then we begin transmission. That's the byte that we read. Then we read the number of bytes to send. And then we read how many bytes, or we loop through how many bytes we're going to send. And we read each byte and we write it out on the line, and then we end the transmission. Okay, so I think our next step is to hook up the logic analyzer and take a look at the data. Unless we think, I'm going to check this again. SDA is the bottom one.
I wonder if it's pull-up related.
Aren't there already pull-ups on here though?
Yeah, they pulled up to 3.3.
And this is 3.3 I have it connected to. Or do you think the output on here is 5?
Oh yeah, maybe this read on that board because it has an ST micro, right?
It is an ST micro, yeah. So it would have to be 3.3 volts. Okay, Jeremy was just asking maybe it's power related with pull-ups, and it might be, but RX is SDA, which is purple. Purple is connected to the middle one. SDA. So SDA is connected to SDA, and SCL is connected to SCL. All right, let me grab my logic analyzer, and we're going to probe the data and see if data is actually being transmitted over I2C at all. Okay, I'll be RB.
Sometimes that works out a little easier than you think. Especially when you're dealing with wires that are been soldered about 3 or 4 times now. And I can't really trim them because I will lose the length I need to go underneath here. So.
There we go. Sorry, I just had to turn the lights on in my office from my phone because I have them set off to turn off at a certain time. All right. So let me show you what I'm opening up here. There we go. This is my Saley logic analyzer. So if you guys are ever interested in learning about communication protocols and like how computers or how things talk to each other, get one of these. It's made by the company Saley. I met with the guys actually at Maker Faire a couple of years ago when I was doing a presentation there, and Alan and I were invited to their office to go meet with them, and they gave me one of the 30 or the 16-bit versions of this, but Jeremy stole it, so I got the 8-bit version now. But with the 16, boy, was it ever cool! And believe it or not, the 16, like I used it quite a bit. I needed the 16, but so here's all the wires that you get, and this is 8-bit, which means you can hook up 8 different wires with these little connectors, and you can actually watch data and decode data across devices. So if you wanted to see, say like you had like a serial device, right? Like, I don't know, or I2C in this particular case, we're going to hook up the lines to it, and then whenever data goes back and forth, we'll be able to see that dictation data in the software. It's pretty wild. So the black is not actually ground. The gray is ground. And it's marked ground, just so you know. So what we're going to do is we're going to hook up ground. This is going to be a little difficult. We might have to solder some more wires to this thing. I don't even know where the ground is. It's going to be tough for us to find a ground. Okay, here's a ground here. Let me show you where I connected this. Can you wait for the focus to hit here? No focus?
Adjust the channel to make sure it's smooth and down.
Come on. There we go. So see there's a plus here and there's a negative here. So all I need is a ground to be shared ground. You know, on the forum you always hear me talking about sharing grounds. There we go. The ground is a neighborhood bicycle. Just as Awesome Power says. Everybody wants a ride. Everyone needs to be connected to ground. Next is we're going to hook up this one and this brown wire. Okay, Jeremy's music is starting to get really bad. You guys probably can't hear this, but it's like, I don't know. It's terrible. Okay, so we need to hook into the SDA and SCLs. So we know purple was our SDA. So we could probably reach it from here. Looks like we can.
Whoa, looks like I can't even skip. I used up all my skips because I'm on free.
Shut up. Spotify doesn't even allow you to skip songs if you don't pay for it.
That's true.
Wow. You know, considering you get a Spotify family plan and you can put I think it's like 6 of your friends or something on it, and it ends up costing people $2 a month. I think we calculated. So I'm not obviously doing a Spotify promotion here, but for $2 a month, I have a family plan. I don't have any more family for you, Jer.
I just noticed that I made a mistake. I did not
Okay,
notice that
so
before I did the
I do have only one problem, guys. I don't know if I have enough USB bandwidth to make this happen. If I can get another USB hub on this side, we should be okay.
I have to break that off, re-glue it once this is back on.
Okay, so I have another USB hub I found.
Today's just not going my way.
I'm just going to plug it here.
But, let's see if we fix this.
We got to get you a wireless lapel mic,
Yeah, I was thinking about that.
so you don't have to yell into my channel.
I priced it out. It was about $50.
Oops, I lost us here. There we go. Okay, so let's see if this is going to work. A lot of USB hubs hanging off this thing.
Let's see what.
Okay, we got a COM port. Oh, you can't see what I'm doing. I'm on my computer. So I'm just checking to see if we have a COM port, and we do. Somehow we have 2 COM ports. I'm guessing this is the right one.
Their values are going to be.
Let's try this again. Let's add in our connection control here. EZP connection. 7. There, okay. So because we changed the USB port that the OpenCM is plugged into, because we plugged into a hub, we now have a different COM port. And now we're going to plug the SALE in as well into this. And I got a lot of stuff going on here now. All right, we got this mess of wires. Let's show you my desktop. All right, now let's load up SALE.
Interesting.
Oh, I don't have it installed. Logic. There it is, Logic. Awesome. All right, so it says here that we're connected. And you can see here that we have this connected as a serial port. So over, oh, you can't see what I'm doing. Let me make this window smaller for you. There we go, like that. So right now I have an analyzer for a serial port. We don't want that. So I'm going to disconnect that, remove it. We're going to add a new analyzer, which is I2C. And we're going to say channel 0 is SDA. That's what we had it set for. Look at that. And SCL is channel 1. Great. So now we click Start. Now it's set to start recording the second you see there's a value here, which is your trigger. As soon as it triggers, it's going to start recording data. So we'll go back to here. And we'll connect to it. So now we've connected to the device. And just make sure. Okay. Oh, it's having issues with the sample rate we're trying to record at. That's because the USB has not much bandwidth free on it right now. Let's see if we can. We don't need this many million samples. We can probably get away with 1 million samples for like 1 second is lots of time. Let's try that again. The analyzer needs at least 2 megabytes to ensure proper. Oh my. Okay. Okay, it's going. Let's try this again. So we should be able to click on here, click on here, click on here. There we go. Do you see? This window went away. There's our data. So let's zoom in. Look at that. So there's our data. So we set up a write to 0x40, and then we wrote a bunch of data to it, which, ooh, and then there's another write. See, this is a stop and start. So you see these? These are stop and starts from the I2C. So there's a lot of stop and a lot of starts. Wow. So we're writing 0x40, some values. Huh. Let's take a look at our code from here. Just make sure that we're doing things right. Set the I2C address. Start. Let's take a look at an example again here. Let's go right. So we start our begin, which we know is happening. We begin transmission, we write some data, and we end transmission. And in here, I2C initialize, so we only send this if we're not initialized. Then we begin from the first byte, which we know is working, because we see it here, right? You see this is 0x40. That's the address. Oh, do you notice that every one of these has a NAC? Is there an... Oh. Hold on. I'm going to keep saying oh because I'm going to check. There's a NAC too. Zero X40. It seems like this particular protocol keeps sending to 0x40 over and over again. Rather than one just giant packet. Okay, no problem. That shouldn't still be an issue for us. I wonder if there's a write. I wonder how you... So there's a NAC and an ACK. And... begin. I wonder if there's a way to do that. Let's do a quick Google search. Because I remember reading something about that before. Or maybe not. No. Okay, it might be pull up and pull down related. Let's look in here, settings. Because we know that the reason why I know that it's sending to the address is because you can see here that's A0. That is the address indeed of the device. It just doesn't seem to be. Let's move these ports or these connectors from here to here. And see if we can, the data is actually getting sent all the way to this thing. Because maybe one of these wires is broken or busted. You never know. Oh, it'll be hard to connect this to it. Oh no. We might have to solder again, everyone. Oh no, solder time. Or I could just hold it. I'm gonna have to do that. This is harder than it looks. There. Oh, geez. Okay. So let's switch over to the desktop. And hold my hand on here and do a logic analyze. And then change this. There we go. There's our data. That's not any data use. That's nothing. We can't read that at all. Let's try this again. So start.
Okay.
And look at that. That doesn't look like data again. It looks like a mess. Oh no. A0. And then some. Okay, that's us moving the slider. And if we zoom out and then zoom into the over here, there's another value. A0. Okay, so we are getting data right to the device. So let's think for a second. I2C is so finicky. So we can stop looking at our code. Is there a way for us to see if the data was actually sent? Let's check the manual again for wire. Does write return, can we check and see if data was actually written? Oh, here we go. Write will return the number of bytes written, though reading that number is optional. Yeah, that's right. Well, good. Then let's do something with this. Maybe it's not actually writing any bytes. Boom, 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 right? So why don't we, when we write,
Alright, let's reglue this bad boy.
let's check. Let's say if wire doesn't equal 1, then let's just halt forever. Okay, because then the system will lock up, and if we know the system locks up, we know we reached a this condition. Okay, so let's disconnect from this, because there's no real debugging on the Arduino, because we're using the serial port already for the communication to Cynthium, to Easy Builder. So, okay, here we go. So we'll connect to it. Good. Now you can see here's our D8 is lit up, right? Because we should be able to drag our finger out here, and yeah. So now when I go to write data to it, and I go back, this D8 should be, there it is, it's disconnected. Okay, so we indeed are not writing to the device. I wonder if it's a pull-up related incident. Because it is an ST micro, and ST is kind of finicky sometimes with I2C.
Pick is better, but yeah, ST has issues.
So, let me think. We might have to do something with pull-ups. The chip on the RGB LED side is a microchip pick. So it's pretty decent. They're pretty robust when it comes to I2C. However, the ST micro is not. It's a little finicky. And depending on Arduino's, or in this case, Robotis' implementation of the I2C library, it could be having some pretty big issues and timing out, or who knows. Are there any pull-ups on the OpenCM board? No, I doubt it, because there couldn't be, because those pins are also used for UX, TX, and RX serial ports.
I guess you could change the ones on the pick side, make them stronger pull-ups.
Yeah, let me think here. The only thing about getting back to Calgary this week is my time zone change is like kicking my butt right now, because it's like almost midnight for me right now. So I start to fall apart and turn into a pumpkin. So we have 25 minutes left of my sanity before you're going to see me fall asleep and clunk my head onto the desk. Let's go back to our code here. All right.
We've done it. Okay, let's go back to that screen.
I'm going to Google for something here. I'm going to Google for Arduino I2C NAC ACK. See, check whether device acknowledged an I2C. This will be interesting. You guys are going to have a hard time reading this, so I'll zoom in a little bit. Oh, look at this.
Okay, there we go.
This guy's code looks fine. He's beginning a device address, writing the address, looping through, writing the data, then ending transmission. But this guy is saying, looking at the wire library, your data is only transferred in the end transmission function. Before that is only setup functionality. Setting address with begin transmission and copying data with write. This function is called by end transmission calls write to and returns the result of that call. So you can check the result, but there seems to be no reason to check at other points of your code. There's no communication yet. Is that true? The buffer is only 32 bytes. That means you cannot send 64 bytes at once. When the slave did not acknowledge to its address. Oh, interesting. So that shouldn't be a problem, though, because we're not sending 32 bytes, but it Is that true?
Okay, so we can go back to testing this one.
Let's see if I can zoom in here.
But you know what?
What's this guy asking about?
I'll test this one
It
first.
says that end transmission can return one of the following codes.
I'm very curious to see if it'll be working now.
How come we don't find any of these
Pretty
things?
sure it will be, but
Other people are finding some great stuff. Did we miss it?
that in the center.
Oh, look at that. We did. Success. Data too long. Receive NAC on transmit of address. Receive NAC on transmit of data. Other.
Close to the proper value. Yeah, it's working now. It's a beautiful day.
Interesting. Receive NAC on transmit on address.
I'm gonna find
Other error. Okay.
maximum value.
Is that ever crazy? So, from what I'm understanding, is that when you actually, you're not actually sending data directly to the I2C hardware from an Arduino. You put it into a buffer, you're writing it into a stream, and then some other system handles writing it out to the hardware once you do an end transmission. If that's the case, okay, then why does this code not work right here? Right? Why is it locking it up? Because it should always be able to write that data.
Yeah, like 109 would be our max on this side.
It should never not be able to write it.
So let's change our maximum value. Min is going to be 40. And then max
Hmm.
109.
Interesting.
We'll go 108. Just be safe. Yeah, 108 is fine. Well, we'll go 1 more. Yep, that's good.
Okay, this is super bizarre, guys, because according to this documentation, and seeing here too long and fit and transmit buffer, and based upon everything I'm reading, ends a transmission to a slave device that was begun by begin transmission and transmits the bytes that were queued by write. Oh, so they are queued. It says that right here. Although, as of Arduino 1.1, end transmission accepts a Boolean argument, changing its behavior for compatibility with certain I2C devices. Stop. True will send a stop message, releasing the bus after transmission. False will send a restart, keeping the connection active. Oh, I think we want to send a stop. We want that to be a true. The default value is true. Oh. I mean, we can try sending it a false. Right? I mean, it's not going to do any damage. Let's try it then. It was begin transmission or end transmission we were just reading about, guys. My brain. End transmission. False.
Wait for that to cool down. We'll test the other side, make sure that's all working again. Looks like we need to,
Okay, let's read a little bit about begin transmission too. What documentation do we have with this? Begin a transmission given. Subsequently, queue bytes for transmission with the write function and transmit them. Huh. Okay, so don't you find it kind of strange if it queues bytes that this could ever never return the number of bytes written? Wouldn't it always return the number of bytes written? Right?
good. Let's test this side again.
I mean,
I'm sure this will be the other one.
it's queued, right? It's just right into a stream, so there's no actually, there's not actually data. Unless we're filling the buffer.
So this one should be D0.
Okay, well, let's go to our code. We can remove. I feel confident that we can remove this if wire code here, because I don't know why it would ever not work though. So I2C initialized. Begin. I think to myself here for a second. Okay. All right, here we go. Let's program this with end transmission being true. Let's see what happens.
Yeah, I think that's good. 147. And so this will be.
I hope you guys get a newfound respect for how much work it is to program stuff with I2C and make hardware work. It's I2C sucks. It shouldn't though. It's just really good at sucking. If it's gonna do one thing it's really good at, I guess sucking's the thing. Connect. Sweet. Okay. So this is just writing some data. 0 whatever. Right? I don't know what it's going to do. Let's just try it. And this is still working. Of course, nothing changed on here because I just wrote some random garbage out. Let's hook up our pins back to here. Because we know this is actually working, therefore we can log some data. What if we hit execute? There we go. Okay. So now let's look at what happened with our data. So we sent our address, then we sent some data. Oh, look at that difference. Do you remember before it kept resending the address over and over again? It's not sending the address over and over again. It's just sending the data as one big stream. Whoa. That's crazy cool. Do we have a stop at the end? There is no stop. But there is always a start. I am super surprised to see this. Okay, let's disconnect from this and let's go back to our code. And let's put this back to a true, which is default state, and reprogram it again. I'm curious to see what the difference of behavior is. Okay, and connect to it again, and start our analyzer, and execute our action. And there, so we see our address is 0x40. Ooh, this is very different behavior than we had last time. And we have a stop at the end, see that? So what we just did there is what we want. Okay. We can, how we played earlier, by locking up, if there was an error, we can try that. We can say if it's not a 0, lock up on end transmission. So we can say if is not a 0, then we'll lock up. All right, we disconnect from it again, and let's upload this data and see what happens.
Okay, so this one's in there tight. This one is a little loose, so I might.
Oh, expected primary expression before a token. Oops. Yeah, we should probably put some sort of value in there, right? There we go. So remember, 0 is, oops, where are we? This one here. 0 is success. So if we're not equaling 0, we should lock up. And here we go. Clickety click. And watch this over here and see if we locked up. We did. We locked up. So that would tell us that it's one of those values. Let's check it for a 1 then.
Yeah, that'll work. Just need a bigger screwdriver.
See if it's too long to fit inside of the buffer. Because maybe that's going to be our problem this whole time, that we have to, in our code, split up the transmission into smaller pieces because the buffer is too small. All right, here we go. Let's just log the data too and see what we get. Execute.
Okay, so let's make some.
Okay, now keep your eye on the D8 here.
See how this
Yep.
goes.
Did you see that? We did it with a 1, meaning if it doesn't equal 1,
Turn it a little bit, or else it's gonna run.
let's say if it's greater than 1, we'll lock up. Okay, that way we'll get success in there, and the data is fit too long in the buffer. No. No, that's not going to help us. Let's say if it's,
Turn this a little bit.
yeah, greater than 1. So we won't lock up if it's
Good there.
a 0, 1, but we will lock up if it's any of these.
Turn a tiny bit.
That way we can get a better idea if it indeed is a 0 or it indeed is a 1 all the time. Because these other errors here is like received NAC on transmit of data on address. We should probably figure out if those are correct or not. Okay, we programmed it right. Connect. And then execute. Okay, looks like we locked up here again as well. So it could have been a 2, a 3, or 4. All right, let's try greater than 2. This is a bizarre way for us to figure out where error actually is occurring. Wish we can just write it out someplace. Oh, you know what? Technically we could. We can use one of the UART ports and write it out. I never thought of that. We would need to hook up something else to be able to read UART, which we can do as well. Oh, look, we didn't lock up. Okay, guys. You see we're still working here? Let's run it again. Yeah, we're still working. What that means is that the error that we're actually throwing is most likely this one, a NAC on transmit of address. Let's load up our calculator and put ourselves in programmer mode. And we'll go hex value. And we'll say 2C. Okay. And we'll go A0. 2C. Yeah, no, that is correct. I was just checking to see if it was 7-bit or 8-bit. So we know that the error we're getting is receive NAC on transmitted address. In fact, we can go like this. If it equals 2, well, first let's start it like this. If it equals 0, then we want to loop forever. So actually, are we getting any success at all? Because success should loop forever. Here we go. Boom. And it looks like, according to this, that we're still running. So we're never actually getting a successful transmission. Interesting. And a 1. And 1 is data's too long. Let's try that one out. All right, here we go. Connect. And we can see that we're working again. Yep. Execute. And we're still working. So it's never anything about the data buffer size. Okay? Because it's never about 1. Let's try a 3. Because we know 2 is for sure going to do it. 3 is something about a NAC on transmission of data. So let's find out what that is. Okay, here we go. And we're working. Execute. And we're still working here. See that? Okay, so it's not a 3, which is transmission of data. And just to make it fully tested, let's also do 4, because I like to be thorough. Thorough. Oh, we got 4 minutes before I pumpkinize. Pumpkinize, that's a verb. All right, here we go. Connect. And working. And then execute. And according to this, it looks like we're still connected because I can still move this. Wow, there's our proof. We are receiving a NAC on transmittive address. That apparently is not a good thing. So let's Google what that means. This guy always gets a result of 2. And this person says it looks like transmission returns the number of bytes sent from the transmission buffer. Okay, this is where we just read already. Whoa, this is totally wrong. Sent. It looks like end transmission returns the number of bytes sent from the transmission buffer, not an indication of success, as this suggests. Ooh. Yes, exactly. It's a wrong implementation of wire API. Could you please file an issue? Ooh.
14 and 15, I think.
No, I'm guessing that because we're always receiving a...
So we will have to replace that.
Wait. We're getting an error message of 2 and 2 bytes are being sent. Oh my gosh. I wonder if this has the same buggy implementation of it. Uh-oh. And here's why I think it might be buggy. Because watch, let's reconnect to this. Oops, wrong port. This port. Okay, and let's turn on our Saley here. And let's execute. No, it's not buggy. Because we're definitely, look, we're definitely transmitting or receiving more than 2 bytes. That's a lot of bytes. Look at that. It's lots. Okay, good. So, I don't think this...
You write down some notes.
Okay, this is not it. How about this one here? Currently returns number of bytes transmitted. Oh, this is a 2015. Oh, this is interesting. Check this out. This guy says, blah, 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 project requires use of some stuff. I have successfully received the data. Send me more data. You should really read the I2C specification. We probably should be. After setting the slave address, when the I2C master sends the address of the slave to talk, a slave which recognizes address sends an ACK. This tells the master the slave is trying to reach is actually on the bus. If no slave recognizes it, it results as a NAC. Well, everybody, it would appear that that's our thing. That's what's going on. It's definitely... We know what it is. So the RGB 8x8, or this thing, not 8x8, whatever it is, RGBIs, is not receiving the command. Now, that being said, I wonder if it's buggy. We can find out. I might have... I happen to have an Easy B right here, and we should be able to plug these eyes into it. And then on my computer, connect to it. Okay. Over Wi-Fi. You won't be able to see this because it's behind the window that it's over here. Okay, so now we should be able to connect to it here. No, you don't want to connect? Why don't you want to connect? Huh. Is something being goofy? This Easy B may not even work. I don't even know. It's just been sitting on my desk forever. Let's take a look at if we connect it at all. 192.168.1.1. 192.168.1.1. Yeah, this Easy B might not actually work.
far this guy can go.
Will it? Well, this is an old EZB. No, it's a new one. Because we can do different things here, like configure startup chimes and stuff like that.
Max would be 135.
But why won't it allow my connection? Connection?
Just in your own one. Maybe I'll separate these so we can see
That is bizarre, isn't it? Nothing here should matter. Are we actually receiving a broadcast from it? Don't seem to be. Let's try this again.
72 is the maximum. Whoops. Minimally smaller value.
Ping it. Oops, wrong port. Was it 8080? We can telnet into it. But for some reason, we can't connect to it.
32.
Is that ever interesting?
And we'll try
Let's try something. Let's go into our settings here, advanced settings, and let's change this communication port to something like, I don't know, 8081. Okay. And now let's take a look at scanning.
Okay, so those will be our new minimum and maximum values. Ones we just wrote down there.
It's just not listening to anything. Anything at all.
Bar.
I think this EZB is damaged.
Try it all out again when it's set up. Throw in a little bit more hot glue.
Weird that it's actually making the noise though when it boots up. It's funny when you go to play with something that's been sitting around for a long time and it doesn't work.
Okay. Let's pop this guy out.
Because we're not even getting a transmission from the broadcast server. So that's telling me that it's not super happy about something. Yeah, I think this EZB is kapoots. We should restart it with this little button here.
I am resetting ECD network configuration.
There we go.
Welcome to the Easy Robot Revolution, the future of robotics. Visit our website for the Getting Started tutorial, www.easy-robot.com.
Oh, you know what I just realized, everyone? I think what we just did is the right thing. I'm guessing that this particular EZB was put into serial mode. So you had to connect to it over a camera port. And I'm pretty confident in that because I think the last time I used it, that's exactly what I did. Yep, that's why resetting it helped. Okay, so now we should be able to hit execute on this. There it is. Yeah, this is working. You see that?
Okay, so I'll just sand it real down. Install it.
There.
Should be on our way.
If you can see the diffusion. So if I go into here now, I should be able to click on this and you can see. You see that? These LEDs are lighting up. Right, and right now they're yellow. Okay, so the thing that sucks, guys, is I seem to always be showing something work with the EZB and never an Arduino. I don't do this on purpose. I honestly don't try to set this up this way. But it just seems like whenever I try to do anything with Arduino, we do nothing but just pull our hairs out trying to get it to work. And then we plug in an EZB and it's just like, poof, it just works. So, that being said, we know that the RGB LEDs work with an EZB. This is not what we're trying to do. Okay, we're not trying to use an EZB. We're trying to use an Arduino, specifically a Robotis product. That being said, let's do a search for OpenCM I2C pull-up. Let's see if they recommend that we put some pull-ups on here. All right, here we go. Pull. The user button. Okay, that's not what we want. The GPUs can pull up or pull down. Okay, it's not what we care about either. A button test. Pull up. No, I want I2C. Here we go. Here's an example of how to use I2C with I2C begin 400. Yeah, do we even know what speed we were dealing with here? Doesn't tell us, eh? I mean, I guess we can calculate it by looking at it, but we're back to here. So 400 seems pretty high. What's default? Like 100, right? Okay, there's an idea. Let's do a begin. Okay, we can get rid of this end transmission crap here because we know that what's going on here. And where we do a begin, let's do the speed. So let's do like, we can go slower than 100. We can go like 50, right? So let's do that. Actually, this is probably the only one we're ever going to use is right here. So let's program this again. And, oh, an error message here. Oh, no matching function? Oh, what is this code we're looking at here? This looks like not serial.print. This does look like I2C. Whoa, what's going on here? What is this? I2C device? I don't know anything about this. Didn't we read somewhere about the speed in here? Didn't we read under begin it passes a param? Oh. Yeah, thanks. Thanks. You're right. The EZB does rule compared to Arduino, but I didn't say that. Let's see here. Address 7-bit slave optional. If not specified, join the bus as a master. That's what we want. Okay, so oh, set clock. That's what it was called, right? Set clock. Although they had some weird code here that showed something like I2C begin 400. Like, what is that all about? I have no idea. Let's just throw that in and see what kind of magic we get. I'm just building. I'm not uploading because I don't want to. I2C device not been declared. That's what I thought. Okay. So we want wire dot set clock, and we'll set it to that much, to 50. So let's put it in wire dot begin. And I don't recall if there was like anywhere specific that we were supposed to do set clock. Was there an example? No. Okay. Accepted values are. Oh, interesting. It's accepted values. Standard mode. Okay, well, let's just put this in there first and see what we get. Program that. Boom, 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 boom. Don't you think that Google's emojis are the ugliest ever? Like, they got some terrible emojis. They look like blobs. I'm looking at Will's smiley face in the chat. Whenever I go to send an email in Gmail using the browser, I'm always like afraid to use any of those Yoda looking. Okay, so let's connect to this. All right. Oh, we're not even connected to this right now. So we said that green was ground, right? Okay, I gotta look at this again and see what we're doing. So green is ground, which is the first pin. And then yellow is power. So that should boot up when I plug this in. Yeah, we saw the LEDs go. And then SDA was purple. Oh, purple is this color. Which color? This one? That's purple. Yes. And then this one is... Okay. And let's take a look back at our pins here. And then we'll go back to our schematic. And just make sure. STA is the bottom one. SCL is the top one. Okay, good. All right. Now let's start our CLI. And let's click execute. Okay, so nothing happened. And but we're still connected. You can see here that I'm able to short out D8 again. Okay. Ooh, we didn't even get any data. Oh, because we're not connected anymore with these either. So connect this. I'm trouble getting these pins in here. Come on. Okay, there we go. All right, let's do this again. Hit execute on here, and then logic should grab it, and there's our data. Okay, so this took from the beginning to the end, it took 9.2 milliseconds to transmit. Okay, and that's with a clock value that we have here. Let's just for fun make this an even smaller value, like super small. Let's see if it's listening to that clock value. And then we'll be able to know if slowing it down sometimes might help. Okay, connect. And let's see how slow this is. So 9 milliseconds, boom. Oh, let's disconnect it again. Oh, that doesn't seem to do anything at all. Look at that. We're still at 9.2 milliseconds. So our code, or this code's not being executed. Could be that. No, because we're not doing any reading or anything, so it can't be run anywhere else. What if we just did this for fun? It said don't do a begin over and over again. Log some data. Execute. Same. No change, guys. No change. So is this what I wanted to do on my Friday night? No, this is not what I wanted to do on my Friday night. I did not want to play with Arduino. I'm going to refrain from going on an open source rant right now, but I don't think it's an open source issue. It's a poor implementation of a controlling board that doesn't have maybe pull-ups on it or something, and they didn't take into consideration how ITC is going to be used. So our clock isn't making a difference. Our wire begin only needs to execute once. Let me think. The thing is, we might have to just put pull-ups on this. That usually seems to be our go-to with I2C. It never actually fixes the problem, but at least it distracts us from what the real problem is.
It does seem it is the problem most of the time, actually.
Sometimes it's the problem.
Yeah, sometimes it is.
But we have pull-ups on this board, right?
Yeah, they're just not as strong as we usually use on ST Micro pull-ups. Those ones are 4.7K, and then on ST Micro boards we usually use like 300 ohms.
Okay, do we have any real 300 ohm resistors? Any like ceramic ones?
Ceramic ones? We have a. You want large? Like
Yeah, like a real one, because then I can just like clip them right onto this.
all resistors are real, DJ.
No, I don't mean like a tiny, tiny, tiny surface mount. I don't want any SMDs.
Okay, I see. I know what you
Like a through hole. Yeah. A through hole. So I guess I better get my soldering iron on. Ugh.
I got my soldering iron. If you want me to pause what I'm doing.
No, I'm fine.
I got all
I'm just extra whiny because I don't want to have to solder anything.
I could do it. It wouldn't take me too much time at all.
Okay, everything's disconnected from everything. All right.
Just pass me that board. We can make that happen.
Oh, you want to put them on here?
Yeah.
Oh, I was going to put them on here.
No.
Why?
Put it on here.
You don't think I should jump across here so that?
Because if you put these in line with a 4.7k ohm, that's going to make it in the middle of both values.
So you think it should be up here?
Yeah.
Okay. So Jeremy is going to put a two 300 ohm resistors on this board. Okay. Rather than putting them on here, because if you put them on here, it's going to be away on the opposite end of the power line, and he says that's going to create problems. Do you normally put the pull-ups at the microcontroller, at the master, or at the slave?
It doesn't really matter. It can go on either side, but it's better if it goes to the master. Because there isn't much resistance in the wire. Maybe a little bit of capacitance. But most of the time when we're working with the accessories, right, we're designing the accessories to have the pull-ups. Some of the accessories are, like chips on the accessories.
It's 10:25 and it's 12:25 for me. Maybe I should just rest my head on this microphone and fall asleep. While we wait here, do you guys want to watch Jeremy? There you go. Okay, so we now have pull-up resistors on our board. Okay, so let's cross our fingers. I'm not even gonna hook up the Sealy. I'm just gonna give this thing power. And cross your fingers, everybody. No, you lied to me, Jeremy.
What?
Doesn't work.
We tried. I didn't guarantee it would work.
You did. You guaranteed me. You bet me your life. You said, I bet you my life.
Let's rewind this.
Oh no, it's recorded. It didn't happen. Okay, so pull-ups is not the problem.
Well, it may not be the right thing, but we would definitely have to throw some potentiometers on there and adjust.
That's too much work.
Yeah, that's a lot of work. Tuning I2C devices with pull-up resistors is...
You don't think they should be closer to the microcontroller?
Like I said, it doesn't matter all that much because resistance of the wire, capacitance of the wire is not very much.
I mean, there's a lot of wire here.
Well, I guess it is pretty long, it's true.
Yeah, like I have a longer wire than I normally would for I2C.
I guess you can desolder those ones off there and put them on this.
You know what? I have this.
Okay. I think we have our values here. Save that.
That's not going to help us.
Go down to 60. Yeah, that's fine. Okay.
So maybe it's because we have too long of
Longer.
an I2C wires. So to get around that, we might be able to just go like this. Like that. Let's try that.
Okay, so let's adjust the one.
Nope, that didn't do anything. Let's flip this around. I don't know which SDA was.
94 is good.
Nope.
Oops.
Nope. What a absolute waste of an evening. Hey Brian, we sold Easy Robot's hardware division. So Easy Robot entirely is gone. It's now a different company called Easy Robot, but it's owned by National Robotics, and we kept the software, and now we focus on software, so that we can have more customers than just having a single customer like Easy Robot. Right, so that's why we're working with Robotis, and we're working with Latte Panda and a bunch of other hardware vendors. So you'll see a ton more hardware being supported by our software. Yeah, no problem. I know a lot of people have questions, and I've been answering them on the forum, and as much as I can as they come up. People are somewhat confused, but if you think about it, imagine like Microsoft made computers, which they kind of do, but imagine at the very beginning they made computers and they made software. It did end up like Apple, right? They'd end up making an operating system for their own computer, and that would limit their market size significantly. And I believe that there's so much value in our platform and the software that limiting it just to Easy Robot prevents a lot of people who don't want to use Easy Robot from being able to experience the true power that the platform provides. Today, we're working with a robot from Omni Labs. It's a telepresence robot. And once we got the firmware written, which wasn't very much work, it took us about half a day yesterday to get the firmware. Once we were done, we had the robot following and tracking balls and doing speech commands and everything within seconds. Like it just how easy it is to use the software, right? And it's super exciting when that happens, because I think about all of the companies that normally would miss out on the potential of people truly experiencing their hardware if they didn't have the ability to access that hardware, right? And Cynthium allows people to access features of hardware that normally would take a ton of code to write. I mean, I think it's great that ROS and C++ and Python and all those programmers are adventure enough to do so and tackle it. But I think it's a lot of work, and not everybody wants to tackle that much code. Somebody on YouTube commented and said, it's really neat that you have this robot tracking a ball, and you described what it was doing. And I said, yeah, that's exactly what the robot was doing. In his mind, he was trying to kind of grasp the concept of how much work would have gone into it, right? And I don't want to downplay the amount of effort that goes into the platform, but it was 3 mouse clicks to make the robot track a ball in our software right? Like it's 3, not 3 clicks, but like 3 options I had to select, and which total maybe was like 8 mouse clicks, but most people would want to write that in ROS or with Python interfaces and stuff, and it might be 2,000 lines of code, right? Circuit Python, I haven't seen Circuit Python. I can definitely take a look at it and see if they have a partnership program where they like to work with other vendors. One of the things to all of you guys that are listening right now and watching, if you ever come across a hardware product that you think that you'd like to see Cynthium control, whether it's a toy or it doesn't matter if it's a WowWee robot or something, don't worry about contacting the company and asking them, because that allows us to be able to work with them closely, right? If they're open source, that's good. I'd like to know what their financial model is around it too, just so that we can understand what we're getting into, because in a couple of the companies in products we tried to support that don't have a lot of, and actually this is a good example, that doesn't have a good financial model around it. There's not a ton of resources or support. So for me to sit here on a Friday night on my own time, even and drink 1 beer and hang out with you guys is fun. But if it worked, because it was properly documented, or it had because who knows what I'm dealing with at this stage, right? It's not pull-ups. We're experiencing a ton of ton of issues with this I2C on this device. So when you were dealing with something that the companies and people are getting paid, the quality of what you get is 1,000 times different, right? Versus working with something open source. When I had more time, yeah, you got to pay the bills. When I had more time before, even Easy Robot, when, the last company I was working for sold, I was able to sit at home and play with electronics. And I loved solving problems like this because it would take me days and days to do it, sometimes weeks. And it would feel fun. But, my friends would come over, they'd scratch their head and look at me and be like, you spent like a week doing this? Why did you do this? Right? And it was just for me. But I don't have that time now. And I think there's a lot of people out there like me who don't have time to tackle this kind of stuff. So working with products and platforms where there's a financial model behind it, you get such a different experience, and that changes everything. So we don't mind working with open source stuff. It's just hard for us to spend a ton of time on it. A branch of MicroPython. Oh, cool. Okay. Well, that's neat. I think supporting hardware right now is definitely my focus for the company. I'm trying to lead the company and partners to support additional hardware, not necessarily compilers or software. So if there's a robot out there, like like the robot we were dealing with today, with the Omnilabs, it's called. I think they have a really great platform, but what they were doing was releasing SDKs and APIs for people to develop with, and that's, I think, significantly limiting on what you're going to get. When you're giving people APIs, you're expecting people to do two things: one, program; two, be creative. Right? Those two things don't really go hand in hand. If they did, you wouldn't see so many robot companies suffering. Right? You wouldn't see. You would see more engineers who actually are artists, and that's not the case. You don't see a lot of artists and engineers. They're two different baskets. They're two different brains, right? You have your left brain and your right brain. Rarely does somebody operate off both of those. So when you can give somebody Easy Builder, for example, they don't have to use the engineering brain. They can use the creative brain. And that's why when you look on our community, the result of what people are building is so different, so vastly different than what most products are being built like, because they're not being built by engineers, right? If most of the engineers on our website, and like people like PTP, they're not building robots, they're building code. They're the ones who are like tackling plugins and behavior controls and things like that. The people who aren't engineers, the people who are creative, and they go, oh, I have an idea. Yeah, giving someone Photoshop doesn't make you an artist. The creative side of Photoshop does, though, for sure, right? I think we have a conversation internally a lot, especially with like our shareholders and the board and everything. And everyone always asks, like, when is the internet or the industry of robotics going to see like the killer app? And it's hard to use that phrase with robots because no one wants to hear the word killer robot, right? Although the Terminator movie is, I guess, come out this weekend, so Jeremy's going to go see it tomorrow. I'm unfortunately not able to, but anyway, I digress. But the exciting thing about when we're going to see the killer app for robots is not being created by engineers, and it's not being created by Microsoft or Google or these big companies. It's going to be created by someone like you, right? Or someone in our forum, someone like Will, or someone like Dave Snuffleupagus. These guys are going to create it. You guys are the ones who are going to create it because you're solving a problem that's unique to you. And I'm a math guy. So when I look at one event, my brain instantly thinks, how many other events like this are happening around the world, right? And rarely is it ever zero. I mean, you'd have to do a lot of bizarre stuff. I remember one time I spent way too much time with a couple of my friends, and we were hanging out, and all of a sudden, next thing I know, we were talking and we were drinking lots, and I was sitting on this couch, and my friend was sitting on a rocking horse, and he was wearing a sombrero, and and I was wearing a hard hat, and it didn't make any sense. Okay, we just started being super silly, right? This is years ago, There's probably only one scenario of that happening at once. It was a good night, Will. That probably only happened once, right? But the example I'm giving you here is that most times, if you think something's super unique, the chances are it's not. So the problem that you're solving with robots is not unique to you. It's unique to probably millions or billions of people, right? As crazy as that sounds. So when when Steve Wozniak wanted to solve a problem for him, he thought it was unique. He was like, I'm trying to solve a problem. I want a computer. And everyone in his life said, why would you want a computer? He said, I want a computer. So he thought, in his limited scope of people he can actually talk to, he thought he was unique. So he made a computer. Guess what? That computer ended up becoming one of the best-selling computers of the world, because outside of his small little world of people, there was so many more. Stories or they could incriminate us. You're right. I'm pretty open, but I think that life is something totally worth living, and definitely not ever sitting back and trying to hide something. I mean, I'll be dead in like 40 years, right? So what's the point of me caring what happens until that point? Because I can't take any of this with me. So especially my stories I can't take with me. So sharing those is awesome. But back to topic, I think that providing the power for people who have problems in their life they want to solve, like taking out the trash or having a robot friend, or a robot being able to detect and log your emotional state when you come inside your house with a camera, just so that your robot can understand if you're happy or sad, and all these things. I think there's so many different applications that I didn't even thought of that I see in the community forum. That's why I know that our platform is going to be leading robotics, and we always have. When we released the robots like the JD and the EZB and stuff, we called that Revolution. Remember that? In 2013 we launched that, right? Jeremy was laughing today because he's been doing a bunch of research into some robot products, and he was laughing because he's like, man, you wouldn't believe how many robots use the word revolution today. Right? Like, it's just crazy. Or how many software programs out there for robotics are trying to demonstrate how easy it is with windowing, like what we do with Easy Builder. Or, I mean, there's 100 examples, right, Jar? Like, of the things that we've done as a company, not just with software, but with hardware. And other companies are trying to copy it. Easy Robot, we had a slogan, build, play, learn. And now you see that everywhere. UB Tech Robotics, they have something similar like that. I don't know what it is, but it's probably something in broken English. Everyone has like this way of being influenced by somebody else. And we've never been influenced by anyone other than you guys, right? We've been influenced by our community who want to solve a problem. And all of the robot companies seem to be influenced by us, which is great. It's a really good feeling. But it also means we can't stop. And if you guys saw what we've been working on this summer, why I've been so quiet, and some of the things that we have, we'll be announcing pretty soon. You might have seen kind of hints to it. So there's been some behavior controls released in the last couple weeks. Some video streaming controls and some other things. Maybe you can kind of start putting some things together, but I still doubt you'll be able to do the whole thing. But it's been a while since we hit you guys with something huge and something new. Build, play, learn. Build, play, learn, share, grow. Yeah, that's UV Tech. That's funny. Will, I can't tell you. I want to tell you. I do. I can't even drop you a hint because I'll start getting so excited about what this thing is. It's going to be good. It's going to be really good. You guys are going to see it really soon. We have a couple working prototypes internally. We're going to do a beta within the community with you guys. It should be up on the website probably the next 2 weeks. It's going to be one part of a 4-step process we'll be releasing over the next number of months. give us a hint. You're our fans. Yeah. I don't like the word fans. You guys are our friends. You're our community. Okay. How do I give you a hint? Okay. I'll give you a hint. Okay, I'll give you a hint. What I've learned watching you guys programming over the last 7 years within Easy Builder is that everyone has an idea of what they want the robot to do. Okay, let's use an example as driving down a hallway to deliver towels at a hotel. As a simple example as that. If you're using ROS or something, you're talking millions and millions of lines of code, right? And in Easy Builder, you're not talking that much code. It's a lot of configuration and a lot of tweaking, and you can make it happen, no problem. But you still are bound within the environment that you've programmed it for. So you program this robot to drive down the hallway and stop at doors and deliver towels. But the hallway color changes. A light burns out. Somebody's in front. There's a beach ball's there. Something super random. Some guy on a rocking horse wearing a cowboy hat is in the way. It doesn't. Who knows? But the fact is that you didn't program for that, and that makes it really hard to program for the world. So what we've been doing is we've been trying to write code and add more code and add more code and add more code to accommodate the randomness, right? It's not real random, right? Obviously, the world there's no such thing. We break things down, but the world appears random. It's unpredictable. That's probably a better word to use. So it's hard for us to write code for an unpredictable world, and that's why robots to date have been failing at so many jobs. So what we're doing and what we're releasing is, how do I say this? Our software shouldn't be about programming what the robot does. It should be about programming what the robot is. And you should be teaching the robot what it does. And if you don't have the time to teach the robot what it does, then there should be people willing to help teach your robot how to do something as well. So that's I think the biggest hint that I can probably give you. But yeah, it's gonna be it's gonna be, I'm really excited about it. And like I said, it'll be a 4-stage process as we release this thing. So we'll be adding features to it. So for all of you guys who are into wanting robots to have tasks and personalities and robots to perform things in the real world, whether it's navigation, whether it's just picking up something and moving it across the room, my dream, which I want to achieve in the next couple months with this project, is to be able to sit in my house on my couch, and I want to ask my robot to go get me a beer from the fridge. And it doesn't matter where I put the beer. It doesn't even matter where the fridge is. It doesn't even matter where the kitchen is. It will be able to happen. And based upon this thing, I think I'm pretty excited that I'm going to have a lot of robots bringing me a lot of beer. So whatever you guys can think of your robot to do too, start dreaming, because we're going to make it possible. So that's as much of a hint as I can give at this moment before I start getting myself in trouble. I think it's just about time that robots are actually doing something cool. Cold beer, sure. If that's the example I came up with. And that's the goal I set for this project. I said if it can do that, if my robot can go get me a beer, then, and I don't have to teach it. I just have to ask it. Just say, go, robot, go get me a beer, and it does it. And you guys are probably like, how the hell is this going to happen? And you'll see. You'll see. Because you'll be part of it. And it's going to be remarkable. And we're going to solve a lot of problems that robots have been facing for a number of years that can't be fixed with lines of code. Just remember that. The problem we're solving is something you can't fix with code. You won't sleep for a few weeks. Well, while I've been working on architecting it and working on tons of effort on it, one of the main programmers behind the whole thing is Amin. You guys really haven't seen too much of him other than his name on the forum, but he's a remarkable programmer that we hired. So we have some remarkable people, right? We have Jeremy, who's quite remarkable with hardware, and we got this other guy, Amin, who's quite remarkable with software. So he's an engineer, so I give him my creative thoughts, and I say, this is what we need to build, and this is how we're going to do it, and I architect it, and then and he builds it. So it's going to take more than him to build the final version, but that's why we're going to need all you guys to use it as much as we can, because the more you use it, the better it gets. Yeah, it is a great crew. It is a great crew. Since we sold Easy Robot, the crew is much smaller, and I don't mind that. I mean, I miss the number of people around, but you have to remember, for the last, like the last 5 years, right, since we launched Revolution product line, right, from Easy Robot, we've had two different divisions of the company. We had two groups. We had people who were working on the software, and we had people who were working on the hardware. And we had someone like Jeremy who was kind of in the middle trying to figure out who he was. And it was hard, right? Hard managing two different groups of people. Because we knew that the true vision of the company wasn't to be a product company. Like, I never wanted to make hardware at all. That was never something I wanted to do.
Oh, so sad.
I made hardware because we had to. The more I made the software do stuff, I couldn't find hardware out there that could do it. Not without like having my own. If you had your own Jeremy, you would have no problem. So all I was able to do is tell Jeremy what we wanted for hardware, and then he can make it, and then I'd write the code that went on the hardware, and then off it went. But most people don't have that ability, right? So we had to seed the market with hardware. And I'm still super surprised. Like when I look online at all the robot products out there that you can buy, and none of them have cameras. Like, are you serious? We've had cameras since 2012, right? Our first wireless camera, and then we went to the first streaming camera that was an Easy BV4. That was in 2013, right? Yeah, 2013. We've had a zero, like I don't know, what is it, like a 2-second latency or 3-second latency, or 3 seconds, sorry, 3 milliseconds or 30 millisecond latency video stream camera on the market you can buy for like, that plugs into an IoTiny even, and something this big, since 2013, and nobody's done it. So we weren't going to influence the market to start building hardware as advanced as Easy Robot unless we were arm's length away from it. So selling Easy Robot was the smartest thing that we could do for the software, because now we can, as a software company, help other robot companies produce some advanced hardware. Look at the timestamps of the videos. I know. I show people that all the time. Actually, I sent to one of our investors, Will, I actually sent one of your videos a while ago too to somebody, because we were having a conversation about robots, and somebody said, "Oh, what's one of your favorite robots?" And of course, I mentioned a lot of you guys, right? And the dates on these videos are crazy. They're 2014, 2015. Like Richard Richard R's butler robot navigating through the kitchen and picking up the canter of wine and pouring a glass and having a conversation with Pandora Bot, speech, right? That was 2014 or 2015, whatever it was. It was 4 or 5 years ago, almost 6, right? Like, you look at all these other robots out there, and I think one of the challenges that we've always experienced as a company, especially dealing with engineers and dealing with like other communities, right? Like look at Hackster, and you look at Let's Make Robots and Robot Shop community and all those kind of guys. They just can't. They don't even want to. They just can't understand. It's almost like I'm trying to think of an analogy as Jeremy's robot falls apart behind me here. Oh, his robot just broke again. Okay, there's a book, Hitchhiker's Guide to the Galaxy, and they land this spaceship in the middle of a field, and there's robots fighting and stuff, and the people are just sitting there, and they call this, and he's like, how come no one sees the spaceship? How come people aren't freaking out about it? And he says it's an SEP, someone else's problem field. And they said there's this invisible field. He said, what do you mean an SEP? He goes, the SEP is a natural behavior of humans, is that when you see something so different than what you can ever imagine, you don't see it. You refuse to actually see it. Your brain just clogs it right out. So the spaceship can land and no one in the audience, in the crowd, could see it because it's an SEP. It's somebody else's problem. So your brain just says, it's not a spaceship, it's not happening, and they just go on with their day, right? An easy builder is kind of like that for a lot of people in robotics, because they try to figure out how something like this could exist, and they just don't even bother. They can't even go to it, right? Because for them, they just want to load up their C compiler and start writing code in ROS. It's like, that's cool. Write your code in ROS. I'm not stopping you. Just like Apple didn't stop people from using a mouse when the Macintosh was released. You can still use a mouse if you want it, or you can code in Unix in the basement, right? And that's the analogy that I like to see our software. When Microsoft Windows and Macintosh was released, those computers weren't in the basements of universities. They were upstairs. They were in the art classes. They were in the journalism classes. They were in the desktop publishing classes. They were, they were in creative writing classes. They were in all the classes of people who you never would imagine that computers would have been in. And the computers that were in the basements, the computers in the basement with the big bearded guys and the sandals and the flip-flops and the ponytails, and those were big Unix machines. Those guys are writing C code and Unix. They're writing the code, the open source stuff for SED and VI and all this. And from that, we got a lot of great things. And you need that. But from the from the offices above, from the classes above, from all the creatives, we got HTML.
Whoa, Jacob, what is on your shirt?
All right, Brian. I think it's enough of me talking anyway, because I think this me talking turned into a way to distract myself from having to actually deal with this I2C issue. So I did tell you a little bit hint of what we're working on. So, and then I talked a lot after that to hopefully distract you from it, so I don't get myself in trouble by releasing too much information. So I am going to sign off, and I'm not going to let this go, this hack, because I definitely want to figure out what it is that's going weird with it. I'm probably going to, maybe next week, the next hack, I think I'm going to write the code for this sensor anyway. I don't think we're going to do it on the OpenCM. I think we're going to do it on an EZB. And if nobody wants to use an EZB for the sensor, then they could figure out how to fix the OpenCM. But I don't see there being an advantage to using the OpenCM at this stage for this one particular sensor. This OpenCM board works really great with Robota servos, Dynamexels, and it works good with digital ports, right? Turning on and off LEDs, and I think that's great for what it is. If you really wanted to control Robota servos and do other things, I think you just buy an EZB, and yeah, that's probably going to leave it for right now. But who knows? Who knows what it looks like next week? Okay, so I'm going to sign off now. Thanks a bunch for everybody for joining, and and I'm going to thanks, man. Thanks, Will. I'm going to be back next week too. So next Friday, I'll post the hack a little bit earlier in the week, so at least there's some time for you guys to prepare for it, to come and join me. But like I said, it's probably going to be hacking that sensor. If not, I have some other things that I want to play with as well. Okay. Well, all right, everybody. I'm happy to be back, and I gotta find my mouse here so I can click the stop button. All right, and I'll see you online, and until then, I'll see you on the website as well. Bye.